Hi, and welcome to this Forge Solar demonstration. My name is Keenan Sims. I'm the lead developer of Forge Solar and co-inventor of the Solar Glare Hazard Analysis Tool technology. In this demonstration, I'll be guiding you through a sample project using the key Forge Solar tools and features. We'll create a new project and site configuration modeling PV arrays and receptors. We'll submit the site configuration for analysis and review the glare analysis results. We'll go back to the editor, clone and modify a new site configuration with changes, and conduct a PV optimization. For this demonstration, we'll be evaluating a fictional PV installation in Hilo, Hawaii. We're going to look at examples of rooftop system as well as ground mount and ground mount with tracking modules. So let's look at our receptors that we'll be analyzing as potential recipients of glare from the PV installation. The Hilo airport east of the PV installation has 2 active runways and an air traffic control tower. We can see one runway going east-west, which we'll model with 2 approach paths, and another runway here with approach paths northeast and southwest. There's also an air traffic control tower to the south that we'll want to include in the analysis. So let's go back to the Forge Solar website and begin the glare analysis. First, we're going to go to our project list. We want to create a new project. Projects act like organizing folders where a project contains many related site configurations. If we have this PV installation, we'll create a new project for it, and it might contain 1 or more site configurations modeling the PV modules, and maybe if we need to make changes, test some variations of the site. Those will all be contained alongside their results in this project. The site we're developing is a larger site, over 1 megawatt, so we're going to go ahead and create a new project. We'll do advanced here because of the project size. Give the project a name, select an approximate PV system size. We can add a description if we want to, but we don't need to. And then we set the correct time zone offset. In this case, for Hilo, it would be -10. And then we create that project. So now we have our project detail page, which displays the parameters we just selected. It also tells us our analysis credits and optimization credits for running glare analyses and optimizations, and other parameters. We can edit these settings if we need to. We can also look at existing site configurations if we had any, open a map editor to start working on the project, and also look at PV optimizations, which we'll look at later, and import data if we had that. But for now, we'll go ahead and open a blank map editor to start working. So we've opened the map editor. This is the main interface for modeling sites for glare analysis. We have component tool buttons on the left. These are how we will draw or model our different components on the map itself. PV arrays, vertical surfaces, and receptor components, points, approach paths, and generic routes. On the right, after we add components, their data sections will be created where we can drill down and edit more detailed information for each component. And then we have standard options at the top, such as looking at our project detail page, creating a new one, doing the same with site configurations, opening an existing one, or maybe cloning the one we're working on, or changing some site settings. Later on, we'll also use the optimization tool. Let's get started modeling the site. To create a component on the map, we use the tool buttons on the top left. In this case, we'll activate the PV drawing mode. We click once to activate that. Now we can start drawing our PV array on the map itself. We draw the PV array by adding vertices or corners. Now I'll start in the top left, the north side of the site. I'll click once to begin the polygon that represents the PV array, and I'll continue clicking to add additional vertices or corners. We can have many of these for a PV array. In this case, I'll model this particular ground mount system with 5 total. So now we've defined a footprint that we imagine would be filled with PV modules, and we double click to close the polygon we've created, or single click on our first point to close it. And that defines this first PV array footprint where these modules will be placed. And it also creates the data section on the right. The data section will include additional inputs and parameters to further describe the PV array we've designed. We can give it a name. In this case, we'll just name it PV ground. If it had tracking modules, we would set those parameters, but this is a fixed tilt system, so we'll just leave that as no tracking. And we would know, in this case, let's say the module tilt measured from flat ground is 25 degrees, and the orientation is 180 degrees. Orientation is measured clockwise from true north, so 180 degrees indicates that these panels would be facing south. If we wanted to, we could go into the advanced options for the PV array. We could select a different module profile for the material. Right now we have smooth glass without anti-reflective coating, but maybe we know that these have an anti-reflective coating, so we'll adjust that. We can provide a rated power for the system if we know it. It's descriptive only, and it's not necessary for the glare analysis and has no effect on those results. So for now, we'll say that we happen to know this one is 2 megawatts. But it would be okay to leave it blank. On the bottom, we have our coordinate data. Elevation values are pulled from Google Elevation. If we have more accurate data, we should use that for the elevation. For the height above ground, it's typical to use the vertical centroid of the panels themselves. In this case, maybe they're around 3 feet. To be more conservative, we could run additional analyses using the lower height of the module edge and the upper height. And we can see that these are the ground elevation and the height above ground are summed to give us a total elevation of each point. The help page on Forge Solar has more information on how these PV footprints are modeled and analyzed. But keep in mind, the coordinates are smoothed so that the PV footprint lies on a single plane. It might not be flat, but it will be planar during analysis. We click Done on that advanced menu, and let's go ahead and name this site configuration. We can name it whatever we want just to help us organize if we have multiple versions. We'll just name this our initial, and then we save. We save so that we can come back and work on it if we need to, and the data will be persisted. So that's our first PV array. Let's go ahead and add a second PV array. Maybe we're also adding a rooftop system near the main system. It could be a large rooftop or a smaller system, but for now, we'll do a smaller one with just a few points. And we're just going to use the southern portion of this sloped rooftop here. For this footprint, we'll just have 4 vertices. Now if I scroll down on the right, in the PV array data section, we can see our second PV array. Let's name this one rooftop. This one will also be fixed, but because this roof is sloped, we need to capture that slope in the module tilt. Let's say we know it happens to be 5 degrees. And it's south facing, so we'll also leave this one at 180 degrees orientation. For rooftop systems, we want to capture that slope in the vertices of the footprint. So in this case, I drew the first and second vertices first on the upper edge. We would want to know what the ridge height is of that building. Maybe in this case we know it's 12 feet, and the southern edge is 10 feet. One thing to be careful of with rooftop systems or parking canopies is whether or not the ground is leveled. The ground elevation data might not be accurate for the location, or we might know something more accurate. Let's assume this building is on level ground, and we happen to know it's 14 feet. Now we can see our total elevations look more consistent. Now going up above, let's also change the module surface material to include an anti-reflective coating. And we're done with that PV array. Notice that that one I left the rated power blank. Now let's save it again. And if we zoom out, we can see we have this larger PV footprint and then a smaller rooftop system. I've activated the pan, the hand, just to move around the map without creating new components. Now that we're done with our PV arrays, let's start adding our receptors. So we're going to pan the map over to the airport. And for this demo, we'll only model 2 of the approach paths rather than all 4. But this advanced project site could contain up to 20 different flight paths if we needed it to. So here we have one of the ends of the runway. Notice that runways typically have a designation at the end denoting the approach direction. In this case, 8 representing 80 degrees. So to model this flight path, we're going to activate the 2-mile straight approach path component. It's just 2 clicks. First, we click on the threshold location, here indicated by the parallel lines. That's our threshold marker. Then we drag a line outward. It doesn't actually matter how far out we go. And we click again away from the runway, showing the approach. The system will automatically adjust the line so that it's 2 miles in length. And if we scroll out, we can see the other point at 2 miles out. So now this receptor represents an east flying approach. If we need to adjust the direction, or maybe the glide slope, which is the descent of the aircraft, we can go over here to the flight path data section, and we see our first flight path. Maybe I'll change the name to FP08. And maybe I was a little off in my direction. It's 90.5. I'll adjust that to 90 degrees from true north. If more accurate data is known, such as from an FAA database, we should always use that over the default values provided. Our help page does have a link to the FAA database, which contains airport-specific flight path data. But that's it for that flight path. Now if I go to the opposite side of the runway, we'll see the complementary approach, and we'll create another receptor there. Again, 2 clicks. That gives us our second flight path. If I scroll down, maybe I'll rename this FP26, matching the designation, 270 degrees, and I'll leave the other parameters. Now flight paths do have an advanced dialog as well. We can modify the pilot field of view. Currently it's set to 30 degrees downward, 50 degrees azimuthal, which restricts glare to within that field of view. So for example, it would ignore glare that was appearing underneath the pilot during flight because they wouldn't be able to see it. These default values are accepted by the FAA interim policy and other aviation authorities, but always be sure to check with the reviewing authority that you're working with. And we could adjust other parameters like ground elevation if we needed to. That's it for that flight path. And save it again. And now let's look for the air traffic control tower. We know ahead of time where that is located. So we scroll to it. For a control tower, here we can see it. The shadow is a good indication of where that tower is. Keep in mind that sometimes the images are taken at a tilt. We want to account for that as we place a point. So now we'll activate the OP receptor drawing mode, which is an observation point. And we'll place a single point with 1 click at the base of the tower. Right now it's labeled as OP1, but now let's go to the data section on the right. If I scroll down, we see our point receptors. And we check the box indicating it's an air traffic control tower, and the name is changed to reflect that. Now, a very important parameter for a control tower is the height above ground. We would need to obtain this from the airport, from our permitting authority, wherever we can. Forge Solar does not have this data stored, so it always defaults to 0. You want to edit that to be a more accurate value so that it represents the eye level of the cab of the control tower. In this case, we know it's 105 feet, so we'll use that value for this demo. So we change that. We can go ahead and save again using the button on the top right. And we're done with the control tower. Now let's say we had a client or maybe a Department of Transportation that also wanted us to look at a nearby road. For that, we're going to use the route receptor. This is a generic path receptor that can model roads, rail lines, helicopter paths, non-standard flight tracks, any sort of path or multi-line segment that we want analyzed as a receptor. So let's scroll back to our PV site. We can see that to the north of it, there's a larger road. Go ahead and model that with a route. So I activate the drawing mode. And here, we just click each time I want to add a new vertex along the route. So I'll start at this intersection, and I'm just going to draw it. I'm drawing it east to west, but it will be modeled as a two-way road. I'm going to add a few more points. Each point we add, the elevation is queried from Google for that point. So we want to have a good number so that we know the elevations along the route, because the system will not be querying in between the points. It will just use the points themselves to create the path to analyze. And I'll go past the PV system slightly to the west. And I'll double click to end the route. We could have more detail on this, adding extra points, but this is enough for this demo. Now if I go to the right and I scroll down, I can see my route receptor data section. We can check a box indicating it's a one-way route. In this case, we'll leave it blank because it's a two-way road. And we have a view angle. This is azimuthal only for the route, so it filters the field of view of the, say, the motorist traveling 50 degrees to their left and right, and filters glare outside of that. If I look at the advanced dialog for this route, we can see that we can edit the various coordinates for the route. In this case, maybe we're modeling car, so we'll put 5 feet height above ground at each point. And we're done with that route. So that's it for the receptors. We'll go ahead and save the site. And one last thing to note, if we look at the site configuration drop down, we can go to settings. A couple important settings here we can use. First of all, maybe we want to run some quick analyses to ballpark the results. We could use a different time interval. The default is 1 minute, so the system is analyzing every single minute of the year to determine glare. If we wanted to run some fast ones, we could change that, although permitting authorities typically require that 1 minute interval. So for our final analysis, we'd want to set it back to 1. We could also set the peak direct normal irradiance for the location. 1000 watts per square meter is a global average, so if we have more accurate data, we want to input that here. Our help page does have a link to some data sets for the US that has more accurate data based on various airport locations. Finally, we could check a box to have our results include an Excel data file for times when glare is found. Okay, so after we made some changes there, again, let's use the button on the top right to save it. And that's it for setting up our site configuration in the editor. It's now ready for glare analysis. Now that the site is finished and we've saved it, we can click the button on the top right, glare analysis. We save before running the analysis and not after. The site will always delete any results when a site configuration is modified and saved to make sure we don't have stale results alongside a modified site. So the general workflow is to create or modify our site configuration, save it, and then analyze. Depending on how many components we have, this can take a few minutes or more, but a single glare analysis could contain, for an advanced project, 20 PV array footprints, 20 routes and flight paths, and 40 points. So we could have a large site. If the server is under heavy load or we don't want to wait, we can click the link here to have the site email us when the analysis is complete. So our analysis is complete. We see that both PV arrays are finished. So now we can view the results. After clicking the link, we're taken to the site configuration Components and Results page. I want to show you real quick how to find this page when you're not in the editor. If we're at our project list, first we see our demo project here. If I click on its name, we're taken to that project detail page. From there, now, if we click at the bottom, the link to site configurations, we see a list of our site configurations. We just created one, and we can see it here. And then we can also see that we have results. The system has predicted yellow glare for one or more of our PV arrays and receptors. So if I click on the name, we're taken to that results page. This page displays and summarizes our glare analysis results and our site configuration. We see when we created and updated it, our time step, our project information, a static map of the site, some functionality at the top right, such as obtaining a report or reopening it in the editor if we want to make changes. And if I scroll down, we have a summary tab. To the right of that is a PV array result tab. If we had any vertical surfaces, such as a glass building we were analyzing separate from a PV array, that would also have a result tab next to it. But here we have our summary table. We see that both of our PV arrays are predicted to generate some glare. Green, indicating low potential for temporary afterimage in observers. And our ground mount system is expected to generate yellow glare for receptors. Yellow meaning it has potential for temporary afterimage. An example of that would be like a camera flash, where the glare sticks in the receptors in the observer's eye for a few seconds. This could be a concern for a permitting authority. They want to make sure motorists or pilots are able to read their instrumentation at all times. So in this first tab, now if we scroll down, we see summaries of our actual components. These are basically copies of the data we've already seen, all the different parameters, the area of the footprint, and the vertex data on the right for our ground mount PV array. Our rooftop PV array system below that, our flight path receptors as I scroll down, our route, and our air traffic control tower, and other site settings and assumptions below. These data sections are all in the glare analysis summary tab. If I scroll back to the top, now let's take a look at the detailed results by clicking the PV array results tab. Here we can drill down into results for each PV array and receptor. Again, we have a summary table displaying our PV systems, their tilts and orientation of the modules, expected results. Notice that for the ground mount system, because we set a rated power, Forge Solar developed a energy produced output. This is just a guide. It's very approximate, shouldn't be used over other more rigorous tools, but it can be used to ballpark when we make changes. The second rooftop system, we did not provide a rated power, so there's no output here. And then on the right, we have links to download those data files that we had the site create, containing analysis information for each minute of glare predicted. Scrolling down, we have a more detailed table on distinct glare per month. This table ignores overlapping glare between receptors and summarizes yellow and green glare expectations for each PV array. Scrolling down, we have our PV and receptor analysis results. Now this section shows the predicted glare for first each PV array, and within each PV array for each receptor. So here we have our PV ground system. We see our 4 receptors and expected glare for each. So our flight paths will have green glare. FP08 is expected to have yellow glare. The air traffic control tower is expected to have green glare, 899 minutes for the whole year. All these values are annual totals. And the route for the road that we created is expected to have no glare from this PV array. Below that, we have some visualizations of these results. First, we have our FP08 flight path receptor. The first graph is annual predicted glare occurrence. This tells us the time of year along the x-axis and the time of day along the y-axis when glare is predicted. So for that flight path, it's expected to be around 7 o'clock a.m. in the morning standard time between January and March and late September and mid-November. Next to that, we have a daily duration of glare, how many minutes per day glare is expected for each day. Next, we have a hazard plot. This is how the ocular impact is determined for each minute of glare. It's separated into 3 categories, green, yellow, and red, which we already briefly discussed. Red is not likely for PV systems because they don't focus the light, so we're concerned with green and yellow. The hazard itself is based on 2 parameters for each minute of glare. The subtended source angle, which is the angle subtended by the glare spot from the point of view of the receptor, or in other words, the size of the glare spot they would see on the PV system. And on the y-axis is the retinal irradiance impacting the observer. This is based on research and gives us our different categories of green and yellow. We have the path location along the flight path versus time of glare. This tells us where along that flight path glare would be visible for the pilot. In this case, we see it's past the 1.25 mile mark out to the 2 miles. Next, we have our sampled annual glare reflections on the PV footprint plot. This is like a heat map of the PV footprint showing some of the positions of the reflection or the glare spot that would be visible to the observer. In this case, we see that for our larger footprint, the northern section is the problematic area causing issues for this flight path. Finally, we have a plot of the positions along the path receiving glare. So this is where a pilot would be as they travel along that 2-mile approach, where they would be seeing glare on the PV footprint. So we can see it's the first third as they're approaching the runway. Now those same results are repeated for each receptor that has glare. Scrolling down, we see FP26 has similar data. In this case, it's only green glare and not as much. Although we can see that on the footprint, it's visible throughout when it is predicted. And for the air traffic control tower, we see that it also is expected to receive glare. In this case, 899 minutes of green glare. This is expected in the evening between 1800 and 1900 standard time. It is green and not yellow, but many permitting authorities require no glare for control towers, so this could still be an issue. You'd want to discuss this with the permitting authority. Sometimes they're flexible regarding mitigation, or maybe times of glare. Maybe the tower isn't used at those times, or they might require no glare of any kind, so the site would need modification to pass. That was our ground mount system. Scrolling down, now we have our rooftop PV array results. And we'll see similar data here. For each receptor, we have our different plots. Scrolling down, we have green glare for our flight paths. In many cases, green glare for a flight path is acceptable, so this could be okay. And for our tower, again, we have some evening glare. That could be problematic. For our PV arrays, in both cases, we found no glare expected for that nearby road. Now I'm scrolling back up to the top. We have some other features we can use. We could download an aviation-themed PDF, which summarizes the results for the FAA interim policy, which requires no yellow glare for flight paths and no glare of any kind for the tower. It ignores any route receptors we're using. We can also open the site back up in the editor. We can print this page of data, and we can also export our component data to an Excel file. This could be used to make changes manually if we wanted to, say, adjust some of the coordinates, and re-import it as a separate site configuration. Now, because we had some issues with our site, let's go back into the editor and make some changes. So I've opened the site back up in the editor. We see our different PV arrays and our components. We know our PV ground mount system had some problems, but maybe we have the flexibility on this site to, instead of using a fixed mount system, maybe we want to model a tracking system instead. So to confirm, we're talking about our ground mount system, 23 acres. So we have our initial results for this site configuration. We could make changes, such as changing the tracking to single axis, and then resave it, but that would delete our previous results and overwrite everything. Maybe we want those to stay, and we want to make changes in a separate site configuration. So what we can do is go to the menu on the left, the site configuration menu, and go to Clone, Save As. For this site configuration, we will call this our single axis tracking version 2. Now, that's similar to doing save as in, say, a Word document where we're creating a copy of our previous site configuration with a new name. We'll go ahead and change our ground mount system from fixed to single axis. We can see we have new tracking parameters here. I'll go ahead and open up the advanced dialog, which will show all those same parameters together. So we have our tracking axis tilt and orientation. So now instead of representing the angle of the module itself, it represents the tilt and orientation of the torque tube that the modules are rotating around. We also have an offset angle. Our help page has more info on these if you need more detail. For now, let's zero in on the maximum tracking angle and resting angle. The defaults for the tracking system is to have a 60-degree maximum tracking angle, which defines the range of rotation, 60 east and west, for a full tracking rotation of 120 degrees, and a rest angle, which represents the behavior of the modules when the sun is outside the range of rotation. Here we have a 60-degree rest angle, indicating the panels stay in position whenever the sun is outside that range. And we'll leave that at 60 degrees. In a future update, we'll add more backtracking functionality. But for now, the resting angle determines what the panels do whenever the sun is outside that range of rotation. So those are the only changes we'll make. So we click Done. So now on this new site configuration, we'll save it. And now it's saved as a separate site configuration from our initial. So we can go ahead and run it. Our new glare analysis of our second site with the tracking system is complete. So let's view those results. Here we see that instead of having yellow glare as our worst predicted glare, it's only green. Now recall that we changed the ground mount system. Our summary table shows that now it's single axis tracking with green glare, 3,800 minutes predicted annually. If we scroll down, we see that now we only have glare predicted for flight path 08, and that's all of the glare that's expected. For many permitting authorities, green glare for a flight path is acceptable, so we would be done with that footprint. If I scroll down, we see the same results we talked about before. If we wanted to further mitigate that glare, we see that it's mostly predicted for the north portion of our PV footprint, about midway along the flight path for the pilot. Now if I scroll down further, we have our same results for the rooftop PV system because we didn't make any changes to it. So maybe this one, because it has glare for the control tower, I'm scrolling down now through the flight path results down to that control tower. We see that we have that same glare because we made no changes to this PV footprint. So we might still want to deal with that. But overall, we've made some improvements and modeled a tracking system. So in this demo, we modeled a ground mount PV system with fixed axis modules. We also changed it to use single axis tracking to see how that affected our results. And we modeled a smaller rooftop system against an airport and a road. Next, we're going to take a look at the glare reduce optimization tool. From the editor, we can click the Tools menu on the top left, click the Glare Reduce Optimization, and this pops up a form for submitting an optimization. We would give it a name, and it can be any name, descriptive only. I'll just name it Demo Optimization 1. And for the optimization, we have to select a single PV footprint. So we'll click our rooftop footprint. This is for fixed axis systems only, not for tracking. And what we do next is we would input a minimum and maximum tilt and orientation, as well as a step size. And the optimization feature will take those ranges of tilts and orientations and analyze every combination of them to give us a wide range of site configuration results. It doesn't have the level of detail as a single analysis. It doesn't have all the different plots, but it gives us a good high-level overview of alternative configurations we could pursue, which would be useful for this rooftop site if we had some flexibility in the design and construction, because the initial site that we designed was causing glare for the control tower, which might not be acceptable. So for this demo, I'm going to change the panel tilt. We'll set a minimum panel tilt to 0 and a maximum panel tilt. Let's set that to 20 degrees, and we'll step every 4 degrees on the tilt. For the orientation, let's say we had a lot of flexibility there. We could make our modules face due east and rotate around to due west for a 180 degree range that we're going to sample. And let's go ahead and just look at the step size of 10 degrees. So with these inputs, what the optimization will do is it'll look at a tilt of 0 degrees, an orientation of 90 degrees, then a tilt of 4 degrees with 90, then 8 degrees with 90, and then it'll repeat the same all the way up to the maximum tilt, and repeat that same process for the next step in the orientation, from 90 to 100 to 110. So we'll end up with a large group of glare analyses that we can review. So we'll request it. That's been sent to the server, and we can view our requested optimizations by clicking the link displayed here. These can take a while, especially if the server is under heavy load, so the server will also email us when it's done. Now let's say we're doing some other work and we want to come find that link again. What we can do from the editor is on the top left, click the project drop-down, go to project settings, which takes us to our detail page, and on the bottom now, if you recall that link to PV optimizations. If we click that, we see that we have one pending optimization. We see all the different parameters we provided, the name, the tilt and orientation ranges, the name of the PV array itself, and the progress. So our tilt and orientation combinations yielded 114 different configurations, and right now the server is analyzing each one. So we could wait and refresh the page, or go on to other work and wait for that completion email. One thing to keep in mind after we submit an optimization, we don't really want to make changes to the site configuration that we submitted the optimization from, just to make sure there aren't any changes while this is running. So we would want to work on another site or do some other work on the side. Okay, I've received the completion email from Forge Solar, and we see that our progress is now 114 site configurations analyzed out of 114. So we can look at our optimization results. Clicking on the name takes us to the optimization page. On this page, again, we have a summary of our various parameters we selected, and below that, we have color-coded tables of the combined results. These tables have the orientation ranges set in the rows and the tilt ranges set in the columns. Each cell represents a single site configuration combination of orientation and tilt, with the cell color indicating the outcome of that particular PV configuration. The first table is for the interim policy from the FAA. Red indicates that configuration had unacceptable glare. Blue indicates passing. The second table is color-coded for the worst glare predicted. In this case, it was green in all cases. And the remaining tables break down similar tabular summaries for each type of receptor. Flight paths only, observation points only, control towers only, and routes. We can see that the tower glare summary looks similar to the policy summary table, because we know that according to the interim policy, the tower can have no green glare. And if we scroll down, we get more tabular results of our site configurations. Here again, we see the various module combinations, the total green glare, yellow glare, red predicted. And if I scroll down even further, we have a similar table. This one is broken down by results per component. And we can see that FP08 had green glare in all cases, The other flight path had some glare. The control tower also had green glare in some cases. Scrolling back up, that is the general summary of what an optimization can do. If we have a PV array with a tilt and orientation that are causing unacceptable glare, and maybe as we refine the model, we're still not able to get acceptable results, we can run an optimization and see if we can mitigate the glare by pursuing an alternative tilt or orientation of our modules. So that completes the demo run-through of the Forge Solar glare analysis and optimization tools. I also recommend taking a look at our help pages, both the guide and the frequently asked questions. We're adding more content often to our guide for more information on the fundamentals of glare, on setting up projects, configurations, workflow. The help page is full of extra information that can be helpful. So that completes this demonstration of the Forge Solar tools. Thank you for watching.